our ultimate goal is, as you already mentioned, we want to make artificial consciousness, which is like machine that is conscious.
Thank you for joining Once Changing the World, India's first future tech meets sustainability podcast. And today I'm delighted and honored to have with me Dr. Shuntaro Sasai, the Chief Research Officer at Araya Inc. He's bridging brains with machines to enable direct thought sharing between people. His team built a brain-machine system that lets you write emails using just brainwaves and ChatGPT. And they're developing robotic arms controlled purely by neural signals. Before this, he spent years cracking the code of consciousness at the University of Wisconsin, blending neuroscience with artificial intelligence. And he built a system that helped gamers with disabilities to control Fortnite avatars using brainwave headsets. We are basically chatting with a real life neurofuturist. So, Shuntaro, really appreciate you taking time and being part of the podcast. Wanted to start with brain computer interfaces. It will be great if you could explain what a brain computer interface is, both the invasive as well as the non-invasive BCIs, and what are the capabilities of these brain computer interfaces?
Basically, a brain computer interface is a general term describing like interface that connects your brain directly to computer or machines or any electric agents around you. And for that, we usually use sensors that measures electric activities generated from your brain. In past previous researches, in order to increase the signal to noise ratio, which is the quality of the signals, like you want to get a kind of better quality or clear signals from your brain. For that sake, usually people first try to embed the electrodes, that is the sensors, inside your skull into your brain tissue. And that is actually the best way to get the brain signals as they are without any noises. But if you use that measure, you can actually decode a lot of stuff. For example, like you can decode each word you are going to speak, for example, or sometimes you can even decode your intention or your motor actions. Like you want to move your hand, or for example, you want to take the coffee cup to drink. And with these devices, that will help you or help the sometimes help the mainly patients with disabilities with motor control to help their daily life. But I mean, this is a very nice device, and if you get really kind of good help from these devices, but one limitation is that you need to embed your electrodes inside your skull. That is invasive technology, and which is good. But as I mentioned, the downside of this is that you need to actually take a surgery to open skull surgery to get your electrodes inside the skull, which is I think still kind of hard or challenging psychologically and also physically. So we are focusing on non-invasive technique, which usually uses the electrode outside the skull, like an electrode on the scalp, for example here. Or electrode like inside your ear or something. But still, I mean, you don't need to get any surgery to embed such an electrode. And I mean, the consequence of putting this electrode outside the skull is you actually don't get a good enough signal, meaning it's a very noisy signal compared to the signals obtained with this invasive electrodes inside the skull. But we actually got a really kind of groundbreaking finding, which is scaling law of the neural signals. So let me actually explain more about the scaling law. So scaling law is a kind of well-known concept in the field of the machine learning. Probably, I think you already heard of that, but if you, for example, have many data and train the neural network with such a large amount of data, then you can actually increase the accuracy or quality of your neural network. If you increase the amount of data, then you can also increase the accuracy or quality of your network. And our data is really kind of huge compared to the previous trial, which is actually reaching to more than 1,000 hours data only from the three participants. But that will give us very big finding, that is the accuracy of the spoken words in the decoding based on this EEG is actually jumping up with the increase of the data. Like recently, we actually achieved 95% of the accuracy for 64 classifications using the only EEG for healthy subjects, which is way higher compared to the previous finding.
Congratulations to you and your team for doing something like that. So just want to kind of break it down to my audience, that there are two kind of brain machine interfaces. The one is the invasive ones, which you have to embed it and you need like an open skull surgery, and then there's the non-invasive ones, which like EEG. The problem with both have got its pros and cons. The non-invasive ones, obviously you get better signal. The non-invasive ones, you don't get as much better signal. But then with your paper research title, Scaling Law and Neural Data, Non-invasive Speech Decoding with 175 hours of EEG data, we have showed that data is the key. It's pretty much like how Dr. Fei Li's ImageNet revolutionized computer vision through AlexNet by scaling these the image data, and even the scaling hypothesis, with just scaling more with these LLM data, you're showing that there's things are becoming more and more magical. You feed in a lot of data and a compute and GPUs, and the models are actually performing better, and basically the same theory applies over here also. Is what you're suggesting, that the more the data that you have right now, you had only three participants. Eventually, if you have got more data, even via EEG through these non-invasive approaches, you will be able to better understand the data. Will be great if you could talk a little bit more about this paper, the scaling law in neural data.
As you pointed out, the invasive method is actually giving us a better quality, way better quality, and that actually enables decoding with high accuracy, but only with like small amount of data. I guess 10 times smaller. Yeah. But I guess the data amount actually going to compensate for that weakness of the non-invasive recording, which is a signal to noise ratio. So this is a kind of, I guess like changing the way of thinking. Like if non-invasive has a worse quality, then okay, let's just increase the data. Like 10 times more, for example. That would be kind of our, I don't know, magic was attempt, and that but succeeded. So this paper, using this 175 hours data is, I think, only from one participant, and we already have more participants so far. And in total, that is going to be like 1,000 data. But in the original paper, we have shown that of course, there is a scaling law, meaning the quality or accuracy of the classification is getting better and better as we increase amount of data for training. But also, we have found that there is like transferability between the different time points too. So the point is, the scaling law actually is good for training itself, but also it is good for calibration or transferability. And we also can confirm there is a transfer between the time, but also we found a transfer between subjects too. This is actually not in this original paper, but we already submitted next year the second paper. About this transferability between the healthy participant and also between the healthy and the patient. So we got the good transferability between healthy subjects. Like if you collected like 500 hours data from one cohort of the healthy participants. It can be actually very useful for a new healthy participant with only getting a 30 minutes data to achieve like 95%. And this is actually also happened to the transfer between the healthy subject to this ALS like patient. Yeah, whose activity, brain activity, and also whose muscular activity looks very different actually from the healthy participant.
So that's so cool. So here you're saying a that scaling the data will obviously, I mean, help in giving better output, and it's also helping in transferability. With from one patient the data which is collected, it's helping with the other patient also. Can you elaborate on the typical electrode count on your EEG devices? And how noisy are this data? Because you mentioned that when you collect these non-invasive data through EEG, these are very very noisy. How do you go about cleaning this data to make it usable?
Right. So yeah, the point is we actually don't spend much effort to clean up the data. So we first tried like already existing the filtering method that is called adaptive filter, which will basically model muscular activities and also other kind of environmental Gaussian activity that supposed to be added on the original neural signals. Yeah, and we actually reduces such a components from the original signals by using regression methods, which is going to turn those though. Yeah, but that will give us a good the quality of data, but still it is bad compared to the underlying actual neural activities. And we also, the point is, we also don't know what the ground truth because we only have the noisy data, right? So yeah, this is because we actually gave up basically cleaning up the data. And then, but if we can actually get a good accuracy for decoding, then probably it's okay for practical purpose, right? So yeah, we just kind of focusing on the English data.
Shanta, will you be able to explain, like, I mean, when or what's the timeline you see that you would be able to create these BMIs, which would be able to do real time, brain to brain communication? What's the timelines and what are the challenges over there to get to a real time brain to brain communication?
Yeah, thanks so much for asking this. And this is a very important point for our project too. So there are two completely different parts of development for actually achieving the brain-to-brain communication. So A, that is decoding, and B, that is actually encoding part onto the other brain. And so, yeah, the decoding part, I think we can actually achieve until the end of for example, next year, even if that is actually used by, even if we use the non-invasive method, it should be, I think, achievable. But for this encoding or stimulating part, like you actually need to let the other brains to comprehend or understand what this decoded information means, for example. And if you want to actually, if you want to directly like transfer your information to your brain, then you need to stimulate the corresponding the brain area that is responsible for understanding or comprehending meaning, right? But that is actually super delayed. It is very difficult to identify what kind of the stimulus is critical. So far, we actually know that the same stimulus gives you different meaning. You see what I mean? Like there is several factors that determines your brain state correspond to a meaning. So there is a background condition or background state that the brain dynamics originally has, and so if you like put a same stimulus because there's an interaction between your stimulus and background condition that this brain has, and that gives you like completely different meaning. So yeah, we actually need to develop a theory still. So I guess yeah, as for timeline, we actually don't know. Like it will take 10 or 20 more years, I would say.
So you were saying that this research that you did, it was with one participant, and then you mentioned earlier that there was three participants, but it was with one participant you collected 175 hours of data, and this was largely him speaking. It was not thinking, right? Will be great if you could elaborate on that. Whether it was the data which was captured, was it him speaking or was it him thinking, and also the role of artificial intelligence. I mean, with how is the role of AI playing over here to decode this EEG data?
Thank you. So far, we mainly have data during the participants are speaking, but we also have the data while they are thinking about how to put, for example, and we have the conversational data for two people. That means that somebody is actually speaking and the other guy is listening when or try to speak, right? So that is kind of one type of thinking. So we have that kind of data. And we also tried decode the spoken words from the like silent period where I guess the this user or participant is actually thinking about how to describe, how to say, how to like shape the user's intention in words. And but we actually succeeded that too. Like we also found a scaling law for this silent periods too. So yeah, I guess this type of decoder enables us to make like co-pilot for like putting words. That is actually kind of enabled by the collaboration between the LLM and also your brain. So for your second question about what's the decoding, right? Like what AI is actually work for to decode is it is actually learning or it learns the correspondence between the particular brain states or brain signals is what the AI learned by the our AI training.
This has been going on since quite some time. It's not a new technology. Big companies such as Meta, some of the largest institutes, research organizations who are vested in this and trying to kind of figure out or decipher the language of the brain. How this brain wiring and firing these electrical signals brings about our five senses. What's your intuition, because it's clearly this wiring and firing these electrical signals which is the language of the brain, but we are still unable to decipher it completely, though like I said, I mean, some of the largest companies and research organizations are all vested in it. My first question, are there any partnership? And second question is, who are the peers you think are at the cutting edge when it comes to developing neurotech with brain computer interfaces which are actually solving real world problems?
We are actually eagerly looking for a partnership, especially with the tech giants or something, because I guess the most important challenge for now is to accumulate data across the world, actually. So we only have a Japanese data set, for example, but that is not enough for like English or for Chinese or for Hindi or I don't know. So yeah, but for that, we actually need to, I mean, um, our single effort. So how can I say that we cannot make actually this decoder for kind of universal purpose. So yeah, we are going to kind of open our codes and also data in the future, so that we can actually kind of collaborate with the our projects by letting everybody to reuse our codes and data. And but so far we actually don't have any kind of good partnership. So yeah, please collaborate with us if you're curious about that. I'm really happy to collaboration. And for your second question, for example, Meta is like very famous, I guess, a company who invested a very long time for a brain muscle interface. Now, I mean, they are probably focusing on mainly EMG, like it's a muscular activity from, for example, like upper limb or something. Original motivation of our development is not from the other peers or companies of the brain muscle interface, actually. Yeah, because I mean, I'm a researcher and I have a background of consciousness. So I'm very kind of curious about the relationship between the language versus consciousness. Because I mean, consciousness, we have several, okay, super rich conscious experience that cannot be entirely described by using language, right? Like language probably kind of extract kind of essence of your experience, but probably it also drops some or rich actually information that is originally or naturally inside the experience. And I think this kind of embedding into this language, so embedding the conscious experience into language is a very important the problem in the field of neuroscience, and also for a next generation brain machine interface, because current brain machine interface is to produce speech itself, but ultimately we actually want to like share our entire conscious experience to other brain, right? So I guess researching this bottleneck of language is very important, not only to develop the current speech BCI, but also to develop like non-verbal communication type, the BCI. So that's my original motivation. Yeah.
Nobody has, I mean, like a clear cut answer on consciousness, and nobody, I think, has a clear cut answer on when we will have these non-verbal communication, thought to thought, but I think you guys are forefronting it, and there are so many others, and wish you guys the very best. And yes, I think you spoke about Meta is looking at EMG through their wristbands, because they are vested in virtual reality. So through these virtual reality games, you can actually control your game elements and things like that. Maybe the next few decades, maybe we will go from speaking to just thought. I mean, maybe just transferring a thought, maybe not so much a verbal communication, because I mean, if you see, the language also has evolved. Earlier we used to type or keyboards, and then we used to speak, and then now it's more of, I mean, even when we use these lingos, be right back, brb, happy birthdays, hb. So we've cutting down on our conversations, and we've gone from typing with all our fingers on a keyboard to maybe just using thumbs. So I think there's more and more we reducing our agencies somehow, where we are lessening our capability of communication, which is through words, and eventually through the how we are getting into this virtual world because of technology stacks such as augmented reality, virtual reality, mixed reality, and because COVID has kind of pushed us. And then there's artificial intelligence. I'm sure with the evolution of metaverse, where we create these virtual worlds which will eventually will be possibly indistinguishable from or real world, maybe we will be all in this virtual world where we'll be communicating more through thought to thought, rather than speech. Because when we converse, because even right now when I'm conversing, there is so much richness going on in what I actually want to express, but maybe my language maybe inhibits me to convey it eloquently in what I actually want to say. Maybe through thought to thought communication, yes, maybe we will evolve. But I think with every evolution, like every evolution in humankind, with the augmentation, we are also going backwards of sorts. We are regressing because we are losing those capabilities that we used to think was the most important thing for communication, which is speech to speech. But yes, I think maybe I always am a believer that we need to move on with time. So yes, maybe this gradual evolution will happen. I don't know when, but it will happen. Since you talk about this X communication, what are your thoughts? Will you be able to maybe create a world, maybe these brain computer interfaces, where, like you said, it will be very rich. It won't be just voice to voice, right? Maybe with these brain computer interfaces, we'll be able to decipher images, maybe dig up memories, and what are the capabilities you think we'll be able to open up when these brain computer interfaces really evolves? What's your thought? Maybe it will be great if you could just talk about that future which you think what you're working towards.
Oh, yeah. Thank you so much. Yeah, I'm kind of more, yes, I mean, your inspiration is fantastic. I totally agree with your ideas. I mean, that's fascinating, and we should actually try them, yeah, in our project too. But, yeah, so I guess, like, I mean, memory is one of the projects that we can actually try soon, because there is like a memory system that can kind of back up or that can actually be connected to the brain areas, like because I mean, yeah. So I mean, as a neuroscientist, I mean, probably the externalization for memory is kind of difficult if you actually store all the information as data. But if you, for example, just keep triggers that will like evoke the memories in your brain, then that would be probably possible, because that is probably, I think, storing the typical stimulus. But that is a kind of specialized for some type of the information. So that kind of stuff should be, I think, possible, and we can actually try soon. And the for yeah, and in combination with the XR, for example, the mixed reality, it is also possible for to the transfer skills between the experts and the beginners. Like, I mean, we can. So there are, I think, many AR methods already to enhance the practice of the kind of skilled, like sports or something. Like you can, for example, follow the expert's performance inside this AR goggle. And but for example, if you like slow down the that movie of the experts, so that you can actually follow the every, how can I say, like performance, then probably I think you can kind of easily trace what they are doing or what they probably will think while their performance. But at the same time, we can probably stimulate the brain too at the same time to kind of enhance the memorization, yeah, or stabilization of such a practice in your skill. That will probably speed up your practice for acquiring new skills. Yeah, that are, I think, very kind of possible technologies that will come in the near future, I would say.
So then, what are the applications that Araya Inc is going for, which are the low-hanging fruits, when it comes to brain-computer interfaces?
Right. So right now we are focusing on the making the hardware actually. So because as I already mentioned, there's a scaling law, but I mean, to like scale up data, we actually need to get more comfortable or wearable headset type EEG device. So yeah, currently we are kind of focusing on like making the wearable wireless headset, which not only has a microphone but also has electrode inside too. So if you use that kind of headphone in a daily life situation, and if you can communicate with each other with that for like remote communication or something, then that eventually gives you a paired set between the EEG and your voice. that will actually kind of enhance the ability of our brain-computer interface. So that is one thing. And the other thing is actually making the platform for brain-computer interface, because so there are many brain-computer interface already. So, for example, like there is a speech BCI, if it's not practical, but there is such a device, right? And also there are like hand robot or something, and there are for like assistive technologies, we have like eye tracker, we have EMG, and we have like keyboard or mouse are also interfaces, right? But these interfaces are, for example, if that one interface has like very specialized software to install, then it is very difficult to switch in real time manner or seamlessly from the one device to the other device. So yeah, I guess it's very important to develop such a platform that the users can seamlessly switch one inputting device to other, or one outputting device from other, yeah, according to the condition or demand of the environment or computers. Yeah, so that's two things that we are currently focusing on.
We don't have any consensus whatsoever on what consciousness is. There are a couple of theories like IIT, then there's Roger Penrose and Stuart Hameroff, who currently says that consciousness is a quantum phenomena, and the microtubules, it seems, brings up consciousness. So, and then there is this Donald Hoffman and others who say that consciousness is in the universe itself. I mean, it's not internal. What are your thoughts on consciousness itself? Because there's no consensus currently on what consciousness it truly is. Will be great if you can talk about consciousness and maybe some of your research work at the Center for Sleep and Consciousness at the University of Wisconsin.
What I mentioned is so-called phenomenal consciousness, which is basically applied in the IIT, meaning the like consciousness defined as like experience itself. Like you can experience, you have an experience every time, every moment, right? That is a consciousness, is one way of definition, and probably the other way of definition is what you lose when you lose the consciousness. For example, when you sleep or when you dream. Well, dreaming is actually consciousness. So yeah, so when you lose your consciousness, like when you don't have, when you are sleeping without dreaming, or even you're actually drunk and everything is gone, then what gone is consciousness. Is my definition. And I am actually kind of IIT theorist, meaning I am for IIT, like because it is a kind of only theory. I believe to explain the substrate of consciousness with respect to this phenomenon. Thinking about how to experience. Yeah, and so there are many theories I know, but it is the only theory that will start from the consciousness itself, but not from the physical world. Because if you start from the physical world, then there is a like explanation gap. Like, okay, you have all the tools, all the ingredients for consciousness, but we actually don't know why they have not consciousness, right? This is a very famous extreme gap of the explanation. And the IIT is actually going to flip this direction, because it actually starts from the consciousness itself. Yeah, we have a consciousness. Okay, assume that there's a consciousness, or we immediately know there's actually consciousness. But we should actually start from the conscious experience itself, and then we can like assume what is actually connecting your consciousness to the physical world. So that's, I think, the one really kind of promising way to address this explanation gap. That's why I am a theorist, or I love that theory. Yeah.
You and your company Araya Inc, you guys are working on something called as artificial consciousness. So, will be great if you could talk about Araya Inc and what is this artificial consciousness that you guys are working on.
Thank you. Yes. So yeah, we are so-called like AI vendor in Japan. Like we are offering services for AI development for our customers. In the yeah, we have many like experts in the field of machine learning and also in the field of machine learning research too. So yeah, we can provide like many services, and it actually is independent of the customer's needs. Like we can actually make basically any AI for our customers. And so this is the basic business side of what we are doing. And for the research side, we our ultimate goal is, yeah, as we already mentioned, we want to make artificial consciousness, which is like machine that is conscious. Yeah. And so yeah, again, it is actually depending on the definition of the consciousness, but in this case, what we call consciousness is in between phenomenal versus access consciousness. Sorry, it's a terminology too, but so yeah, let me actually explain what the access consciousness is. Access consciousness is yeah, we have an experience, of course. But for example, at the same time, we have a cognitive ability, like we can think, we can memorize, or we can even like process some ingredients that is actually consciousness to think about, right? And the access is this calling this process like we it is assuming that something is accessing to other thing that is a pro experience to elaborate more. So yeah, we have a kind of more, how can I say, the ingredients that is entire consciousness. For example, if you look at, if you think about what you see right now, you can like point out anything. For example, in your room, like you have probably a fair wall or light or something. But if you, for example, ask to say to describe what you look at right now, then you can only say some words, but not everything, right? Yeah, that is a good example of access. Like if you are actually stepping into the cognitive process, the you can use the information only that is accessible for this language process. Like you have more information you should have, like you have more information that is the making your entire experience, but yeah, you can only like describe what you can actually access uh, to this your experience. So yeah, but and the important point is that if you can assume that such a mechanism is in the brain, like there is some part of the brain that is accessing to the other part of the brain, that will probably can, for example, can be copied to make a good architecture for a neural network, like yeah, so meaning the a neural network that has a like global hub of the information, and also like accessed or yeah, partner modules that is accessed from this global hub. And if you can actually think about such a global hub and that kind of structure, then if you look at the neural network from the outside, then probably that kind of neural network can behave as we are. So yeah, that's our kind of practical goal of the artificial consciousness first. But I mean, ultimately, we actually want to implement IIT too to the neural network. Yeah, because IIT, it also has a hypothesis about what kind of structure is important for consciousness, having an entire experience. So if, for example, we can elaborate a spiking neural network or even like a organoid or something that has a like very important wiring diagram, which is for consciousness, then maybe we can develop like actual consciousness, but in the artificial manner.
Interesting, because I think the world, or some of the top organizations, research organizations, are working towards building artificial general intelligence. They are not calling it maybe conscious machines. But yes, I think even right now, these data in data out statistical models are showing emergent properties of what some might call conscious experience, because there have been papers written about these statistical models showing emergent properties. There are just recently, I think Anthropic wrote a paper on how AI is faking alignment. So even these statistical models somehow, which is very, very weird, because they are just you feeding in data and is just throwing out data. But even these models somehow are showing maybe some signs of maybe what we might call like a subjective experience. Is it truly possible to build a conscious machine? Because Roger Penrose, the Nobel Prize winner, Sir Roger Penrose, thinks that we can never build machines that'll be sentient. Are you? I mean, what? What is it that convinces you that we can build machines that are artificially conscious?
The short answer is yes. I believe we can make artificial consciousness. This is not because of my position. I wholeheartedly believe that it's possible. But I actually don't know if like current ways of the development in the field of neural network can actually achieve that. So, but I mean, also depending on your definition of the consciousness, and if that is a access consciousness, probably I think it's possible. Like it can behave as if it is sentient or it has a consciousness, right? Like I mean, there's already a paper that's showing like some LLMs can actually pass the Turing test, which is a very kind of old-fashioned like sign of the consciousness, right? So it is already passed, but then I guess the problem is the what's the consciousness is again. Like if you can actually believe that the one pass the Turing test actually have a consciousness or not. So yeah, that's kind of politics or your belief or something. But for this point, yeah, I actually believe the IoTs to do because yeah, what consciousness means for me is a phenomenal consciousness. And for phenomenal consciousness, IoT proposes a very good way to check if a system has such a phenomenal consciousness or not. And for that, we need to actually calculate integrate information of a system, which is actually information for that system, but not for outside. Because I mean, consciousness has such a property, right? Like we have a consciousness, but that is kind of private. We cannot actually have think about, we cannot actually guess, how do I say, check if she is aware from the outside. I mean, it looks like so, but there's actually no way, right? Because I mean that is a subjective. So yeah, I mean ultimately I believe that we need IoT or IoT-like method to check if it is actually subjective or not. Yeah.
Shintaro, my last question to you. Yes, there have been various benchmarks for these AI and these large language models. Earlier, there was Turing test, and there are so many benchmarks now. What benchmark do you think will be there for an artificially conscious machine? Or what's that fundamental tick mark? How do you understand that? Okay, now this machine is conscious. What would be that capability where you will say that okay, this machine is sentient? That's my first question. And paint a picture of a world, that you are striving to build for, you and Araya Inc is striving to build for. And how do you see that world in the next 10 years?
Strictly speaking, consciousness is completely subjective. So I don't think there's a best way to check whether it is a consciousness, it has a consciousness or not, by using its functions or capability. Because I mean, we can even think about the agent who is conscious but doesn't have any kind of capability or any kind of good function. Yeah, but for like in real life or daily life situation, I guess you can actually assume that your lover, or how can I say, your lover family or something, we believe that they have a consciousness, right? So yeah, this is actually not a good way to describe, but if you can believe that your agent has a consciousness, then I think that is actually a good definition for everybody to think that that agent has a consciousness. And as for benchmark, it's very difficult to propose right now, but we can think about like the beliefness index of the consciousness. It is actually different from like Turing test or any other like function-based test, but directly asking your belief about the agent that is actually having a consciousness or not. And for our second question, yeah, as I mentioned, we are currently kind of focusing on brain-machine interface for speech. And the reason why we are focusing on the speech is that speech is one way, a good way of the making a BCI more practicable. Because I mean, speech is a kind of, how to say, latent representation of our conscious experience, which can be actually used for communication or interaction between different individuals. So if we can, as you already mentioned, if we can use abbreviation always to communicate with each other, that will enhance our productivity. And also we can use such a latent representation for communication with the other agents, meaning the non-human agents like robots or smart home devices or something like that. And yeah, for that, we can actually do in next 5 years for sure. So yeah, we are focusing on that. And but on the top, we also want to make some kind of global workspace like governization of such stuff. Like I guess like if we can have such a system, then we can make each agent have the behave as if they have a big or super consciousness. And if we can actually make that, then this like group of agents can collaborate more smoothly to achieve the better stuff for each other. So that is actually kind of another way of realizing the artificial consciousness or the world that has an artificial consciousness.
Thank you, Shuntaro, for taking time being part of the podcast. I think we're sitting in a fantastic point of time. We are at the cusp of possibly maybe understanding a human brain, maybe 10 years, maybe 20 years, maybe 50 years. This convergence of artificial intelligence with neurotech, I'm sure is going to open up and maybe or the brain as like a book which we'll be able to read. And if we are able to do that, we'll be able to understand these neurological disorders which millions are suffering with. And I'm sure we start with this neuroprosthesis device where we'll be able to maybe help these ALS patients, Alzheimer's, Parkinson's, and paralyzed patient first. And then obviously, I mean, if we are able to read the brain like a book, I'm sure all those neurological disorders, we'll be able to take it out completely. So wish you and your team the very best for this endeavor of yours. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Bye-bye. Thank you.